Okay, we are back, and we are going to start with our periodic trends, which would be uh, just how things change as we move across the periodic table. So, we're going to start with the atomic radius. Now, atoms can generally be considered to be spherical, which is, it's the circle. And the one measurement for the size of a sphere is the distance from the center of the sphere to the outermost portion, which is the radius. So, atomic radius is really just talking about the size that atoms get. Okay, so this is atomic size, not. Okay, so this is the size that atoms get. This is the atom size. All right, now the atomic size gets smaller as you move from left to right in a period. So what I'm going to try and do is keep a periodic table on the screen at all times so you can see what I'm talking about with the trends. The atomic size is going to get smaller as we go from left to right in a period. So we're going to get smaller as we go left to right. So here would be period 3, and as we go left to right in that direction, this is going to be larger. This is going to be smaller. All right, and this happens, okay, because of the increase in the number of protons pulls the electrons closer to the nucleus. So since the electrons are staying within the same energy level as we go across the period, they're staying within, they're not getting any bigger than the outermost electrons, but they're still the same distance from the nucleus. They're relatively the same distance from the nucleus, but the nucleus starts to get bigger, and so with more protons. And so we increase the number of protons, and that causes the electrons to shrink in to the center of the nucleus, so that our sodium over here, our sodium right there, is going to be bigger than our chlorine because it has fewer protons in the nucleus. So then the other common sense one is, well, then how do we move as we go down a group? Well, they get larger as you go down a group, but that really just kind of makes sense. Okay, because as you add additional energy levels, okay, so we're down here with our periodic table, as we add additional energy levels, the electrons are going to get bigger and bigger as we go down a group. But it also just makes sense because our atomic numbers are jumping by a large amount. So either way we go, over here the noble gases are going 2, 10, 18, 36, 54, 86 for that last one. That's a huge jump as we go down. And so it kind of makes sense that everything is going to get bigger as we move further down the table. In fact, anything having to do with size, any size trend, okay, gets larger as we go down a group. Okay, any size trend. So whether it's atomic size or ionic size, which we'll get to in a minute, any trend that has to do with the size, the physical size of the atom, gets larger as we go down the group. Okay, so let's clean that out a bit. Big eraser, wipe that out. All right. So now we have ionic size, which is the other thing, which is once the atom tries to get a charge, or it gains or loses electrons, okay, the metal ions, also known as cations, get smaller than their parent atom because it loses an electron. So we're going to draw that here. A sodium ion is going to have 11 protons, and around it is going to have Let me make. Okay, so that's a better drawing of our sodium atom. This would be a sodium atom. Now, when a sodium makes an ion, it is a cation, and it is going to lose electrons by making a positive charge. It's been a while since we've talked about this, but we did. And so this whole group right here, see if I can get this down right. So, a sodium ion is actually going to lose that outermost layer of electrons. Well, if this is the size to begin with, okay, and it loses an electron to, you don't want to, it's not wanting to erase, is it? Okay, we lose this electron, okay, in that whole outer orbital, this becomes the size of the ion. And so it goes from a larger energy level down to the lower energy level, and it loses that outer electron, and the whole thing just shrinks because it loses the electron. So it goes, a sodium ion then is going to be smaller than the atom, just like that. Well, got to move this up here, get out of the way. Okay. Well, nonmetals do the same thing, except nonmetals, they're anions, and they are going to gain electrons. If you remember, I talked about anions being negative. They're going to gain electrons. And the chloride ion over here, which is just opposite, so here's our chloride right here. Okay, it is actually going to gain one electron, and by gaining one more electron, it's going to get bigger because as being, you're going to be gaining, it's like gaining weight, kind of. Okay, and so a chloride ion then is larger than its atom. Okay, which brings us to ions. What is an ion? Well, ionization is the changing of an atom to an ion by electron exchange. Okay, so the resulting exchange turns the metal, which is a positive metal, into a cation, and the nonmetal into an anion, which is the negative one. Okay? And so by changing from having a metal turn into a cation and a nonmetal into an anion, okay, we have the sodium atom that originally has no charge, has 11 protons and 11 electrons because it's atomic number 11. When it becomes a cation, it gives up one of the electrons. Now, where does it go? Where does that electron go? Well, that electron from the sodium, when it gives up, gets attracted to a nonmetal, and the nonmetal actually gets bigger. Okay, and it will attain a negative charge. So on the next page, we have the sodium ion. Okay, we have a sodium ion. It's got a nucleus in there. It's got a plus 11 charge. Okay, and 11 electrons around it. So it's got one circle of 2 electrons, another circle of 10 electrons, of 8 electrons, and then one last circle. This is the 3s1, okay, electron. It's a 1 electron out here, and this goes away. This one disappears. This outer electron disappears, giving us our nucleus, okay, with the 2 and the 8 electrons around it. And this is the sodium ion, and this whole thing has a plus 1 charge. Plus 1, that's ugly again. Sorry, this is a plus 1 charge on the sodium ion, and it is written like this. It's written as Na plus, or Na plus 1, or Na1 plus. Either one of those, any one of those three is okay. Okay, which then brings us to our chlorine atom, and a chlorine atom does the same thing. The chlorine atom originally has 17 electrons, so it's going to have a 2 and an 8, and another one that's got 7 electrons on the outside. Now remember, these are the valence electrons that we're talking about, and the valence electrons, back from the last lecture, the valence electrons are the outermost, are the outermost energy levels. also known as the highest energy level s&p orbitals. So for chlorine, those 7 electrons would be 3s2, 3p5. But when it gains the electron from that sodium, it changes this 7 to an 8, and this electron configuration becomes, instead of 3p5, becomes 3p6. All right, so the chloride ion will actually get bigger. It'll get another electron, and it'll have this negative charge, making it say chlorine minus, or chlorine minus 1, or chlorine 1 minus. All three of those are okay. Now, before the bond, and these will actually bind to each other, okay, the atoms have no charge, and ions have either a, okay, before the bond, the atoms have no charge, but the ions have either a positive or a negative charge because they've either gained or lost electrons. After the bond, the produced molecule shows a 0 charge. It's actually not a molecule, we'll call it a molecule for right now. This shows a 0 charge, and the bond is held together by the positive and negative charges, called electrostatic attraction. This is a key word that I want you guys to know and learn. When positives and negatives get together and they attract each other, okay, it is called electrostatic attraction. And this is what holds our positive and negative ions together. Okay, now, there's a new one called ionization energy, so let's get rid of those lines. And the next trend is called ionization energy. Ionization energy is the amount of energy needed to remove 1 electron from an atom. Now, some of them are easier and some of them are hard. Please don't spend too much time. No, wait, that's in a different speech. Some of them are easier to pull electrons away. Some of them are harder to pull electrons away. Now, energies are lower as we go down a group. The energies are lower as you don't go down a group because the inner layers of electrons shield the outer layer from the attractive forces of the nucleus. So all those positive charges inside are getting sucked up by all of the electrons in between the outermost electron, which is the one that's going to get pulled, and the nucleus. And so let's say you're talking about a 55 electron atom, or number 55, which is I think it's cesium. So why do I have to keep looking hard for cesium? I can just throw it up there and get, oh look, there it is. There's cesium, it's number 55. Okay, so that 55th electron is way up there on its own. It's that 6s1 electron. It's hanging up, and it's got 54 electrons inside of it that are protecting it from the 55 proton nucleus. And so what it really only feels is a pull of a single proton, a +1 of that single extra proton. And it's 6 energy levels away. So the further away it is, the easier it's going to be to pull that electron away. Right? So the energies then increase as we go left to right, because as the number of protons increases, it increases our nuclear attraction. So for the same way that atom size gets smaller, as we go this way across, our ionization energy okay, so the energy to pull an electron off is lower down here, smaller ionization energy down here, larger ionization energy down here. Even though the size is large to small, because these are larger and these are smaller, the ionization energy over here is smaller, and down here it's larger. Okay. Now, the noble gases have the highest energy removal of all because they're already very low in energy. Okay? And it's going to take a lot of potential energy to move those electrons away from the nucleus. Remember, this is the cringe factor talking here. So if we lift our electron further away from the nucleus, it's going to pull. It's going to need a lot of energy to get it fully away. And it's also very stable, and it's difficult to break up something that's that stable. which bring us to other ionization energies. Okay. By the way, I'm going to let you pause here. I'm going to scroll up. I know I missed one earlier, so we're going to pause for a little bit, and we're going to give you guys an opportunity to answer all the questions that we have on the side. So the first one was on the previous page. Second one is compare the size of the ions to the size of the atoms from which they are from. And then what happens to the first ionization energy within groups and across periods? So we'll pause here, and you guys will fill these out in class. Okay. So, successive ionization energies is referring to the removal of the second and the third and the fourth electron. Okay. So, these require more energy than that first one, because now you start getting into more and more a bigger charge differential, meaning you have more protons in the nucleus than you have electrons around it, so it becomes harder and harder to pull them away. Okay. And because when we start pulling electrons away from easy things, okay, the easier they start trending more towards a noble gas configuration, and it's really hard to pull one away. And so if we take one from the first, from the easiest ones of all, the alkali metals are the easiest ones to pull an electron from. If you take an electron away from it, all of a sudden it looks like a noble gas, and it doesn't want to give another electron away, so it's very happy with what it has. However, the alkaline earth metals, the first one to take away is a little bit harder than an alkali metal. Okay? But the second one to take away is the lowest of them all when you're removing a second electron. And it just sort of goes like that across the group. Okay. Which then brings us to electronegativity, which is similar to ionization energy, and it follows a similar trend, but it's slightly different. Now, the definition of electronegativity is this. It is the relative attraction that an atom has for the bonding electrons in a compound. Now, what are the bonding electrons? Okay, they're the ones that are being shared. Okay, they're the ones that are being shared when you combine your electrons, or when you combine your elements, when they start making compounds. The table of electronegativity was developed by Linus Pauling, and it won him his first Nobel Prize in Science. I think he's got 2. And if you have 2 Nobel Prizes, you are a pretty clever dude. Okay, now, atoms do not always share electrons equally. Atoms will hog them if they want them more badly. Now, mind you, they're atoms and they don't really have wants and needs and desires, but you can consider that those with higher electronegativity are greedier than those around them. Okay, and so one atom, because they're greedy, one atom can have a greater pull on a pair of bonded electrons. Now, this ability to pull on pairs was called electronegativity by Linus Pauling. Now, based on a 4.0 scale, that's the highest one, the atoms with the highest values are in the upper right-hand corner of the periodic table, with fluorine, F over here, is the biggest, baddest, greediest of them all. Okay. Now, metals have very low values, since they don't covalently bond anyway. They don't share their electrons. They give them up. They're fine. Okay, and so it says in our book, see table book on page 184 for trends. Well, here, because I'm that cool of a guy, I am doing this for you. And this is the table on page 84. And look what happens to our, there's an artifact, that's ugly. Okay, to our electronegativity. And these are all of the trends. So atomic size as you go down is going to increase. Ionic size gets bigger as you go down. Ionization energy goes decreases. Electronegativity decreases. The nuclear charge, which is really just the nuclear charge is really just, let's see if I can line this up right. This is really just the number of, it's not going to work. Oh well. Well, that's a fail. That's really just the number of protons. The nuclear charge increases is the number of protons. Okay? And shielding, which is the amount of electrons underneath, is also increasing. Okay, so the big ones I want you guys to remember are atomic size, ion size, ionization energy, electronegativity, nuclear charge. I don't want to line through that. I want you to remember that. Nuclear charge. And along with that, you have atomic size, ionization energy, electronegativity, nuclear charge. Okay, all of those, we need to know these on these trends. You also need to know that the size of cations decrease and the size of anions decrease, and there is a changeover, a rollover right around the group 4 right here, and we'll talk about that at a later time. We'll talk about when we start reviewing this stuff. Okay, so let's go over all these things. So let's move our periodic table out of the way, and let's finish with this. Oh, by the way, you guys do need to sign out. How does electronegativity vary within groups and across periods? And we will pause here so I can pause the video and you guys can record your answer. All right, we'll keep going. So finally, we have the trends on the periodic table. Okay, and let's get the periodic table back. The trends on the table. Okay, if you move across the period from left to right, the number of valence electrons will increase. The atomic radius will decrease. The ionic radius gets smaller with both positive and negative ions, and we'll get into that in a bit. A positive ion is smaller than its neutral atom, and a negative ion is larger than its neutral atom. Atomic number increases, the density decreases, the melting points increase. That should be decrease. There is decrease. The elements become more non-metallic. Ionization energies increase. Electronegativities increase, excluding noble gases, and that is because noble gases don't bond. Okay, noble gases don't bond. Now, if we move down a group from top to bottom, the number of valence electrons stay the same every single time. That's why they have similar properties and why they're in those groups. The atomic radius increases. The ionic radius increases. Atomic number increases. Here's the trend. Okay, so then our density increases. Our melting points increase. The elements become more metallic. Ionization energies, because the atoms are getting larger and electrons are getting further away from the nucleus, the ionization energy decrease. And the electronegativities also decrease because it becomes less greedy when it comes to sharing a bond. So here's the question you guys need to finish with, and your homework is page 178. Numbers 16 through 23. That's what will be due next time. So that is it for the lecture of Chapter 6, and we will spend the next few days going over this and making sure that you guys have got it, because these can get pretty confusing. All right, so I'm going to pause here. I'm going to stop here, and you guys need to answer this question because I think that's number 19, maybe even number 20 in your homework. And we'll see you next time.